I will now invite our next speaker, Sarah Harris, to turn on her camera, and I will introduce her. Hello. So Sarah Harris is a professor in the Department of Earth, Ocean, and Atmospheric Sciences and the Associate Dean Academic in the Faculty of Science at the University of British Columbia. In 2015, she was named a 3M National Teaching Fellow for her massive open line course on climate change. During 7 years, from 1998 to 2005, as a chief scientist at Sea Education Association in Woods Hole, Massachusetts, she studied modern oceans and sailed thousands of miles with undergraduate students. Sarah's current research explores evidence-based science education and how people learn climate science, and which learning opportunities best help people move toward more expert-like ideas about how Earth's climate works. She is a co-author of Understanding Climate Change, Science, Policy, and Practice, and her talk today is entitled, Does Learning Climate Science Matter? Welcome, Dr. Harris.
Thank you. It's great to be here.
I'm very happy that you're here. Would you just let me know, how would you like to take questions during your talk?
You could interrupt if you see questions that we should address right away, or we can take them later, whatever. I will try to have the chat open, but I know that you're going to be monitoring the chat.
Yeah, don't worry about that. We have a moderator for the chat, and I'll make sure to let you know when questions arise. Thank you very much. You can now share your screen and start.
Okay, let's see how this goes. Okie doke.
It's all good.
Great, thank you. It's great to be here. I just want to first acknowledge where I am. This is a picture of the University of British Columbia and where I work, and it's located on the traditional ancestral and unceded territory of the Musqueam people. And those are people who have lived and learned here in this area since the most recent retreat of ice from this part of the world. So essentially a half of a glacial interglacial climate cycle. And I am grateful to live here as an uninvited visitor. I live about 10 kilometers to the east, which is the direction that we're looking, on the unceded territory of the Musqueam, Tsleil-Waututh, and Squamish peoples. So my question here is, does learning climate science matter? And I want to just first say that I come to this primarily as an educator. I'm an educator in formal settings, mostly the undergraduate university kind of setting. And I'm not a cognitive scientist, and I know that all of you here really are, that's your focus is cognitive science. But the work I do is largely in the context of courses, and some of it does involve eliciting student thinking in settings outside, but it's largely in those kinds of course settings. So my work is primarily as an educator and very secondarily as a discipline-based education researcher, and I have been really fortunate to work with some amazing colleagues in that space. Just want to point out that if students are learning about climate science in post-secondary institutions, it's largely from people who are like me or people who are active researchers in climate science. And they're in departments like mine, which is a science department. And certainly there are many other non-science disciplines in which students learn about climate change, but not necessarily are they learning much about science. So I'm interested in whether what I do as an educator makes a difference and how it might make more of a difference. So am I teaching climate science as a medium to help my students be better able to understand and evaluate scientific information? Is it so that they can gain practice dealing with uncertainty? These are definitely really worthy transferable skills in themselves. But will learning how Earth's climate system works actually benefit them? Will they benefit their communities that they belong to? Will it benefit them in some context that they find themselves in after the class or during the class? So that's where I'm coming from. I'm going to use some climate data to tell you a little bit about me. Some of it's already been said in the introduction, but this is a map of global temperature anomalies. It's a map for the 1970s, as you can see, and it's relative to a baseline of 1951 to 1980. And on this map, you can see some parts of the world that during the 1970s were averaged a little warmer than the baseline, and also some places that averaged a little cooler than the baseline, the cooler colors. And this little number in the upper right, this 0.05, is the degrees Celsius, the global average for this decade, how different it was from the baseline. And it's not very different because actually this decade is included in the baseline. It's part of that 1951 to 1980. And I start here because I was actually born a couple years prior to when these data started. And so I grew up in the 1970s, and then in the 1980s, I went to high school, and I completed most of my university time during this decade. And then in the early 90s, I graduated from university, and I spent the bulk of the mid part of this decade going to graduate school. When I started graduate school, the atmospheric CO2 concentration in the atmosphere was about 355 parts per million. And now, of course, it's nearing about 420 parts per million at the annual Northern Hemisphere peak, which would have been just last month in May. And in graduate school, I was studying paleoclimate. I was studying marine sediment cores and what we can extract from them to tell us how the climate functioned in the past, in the absence of humans, how the ocean circulation functioned in the past as well. And then in the latter part of this decade, as in the introduction, I went to work for a really wonderful nonprofit called Sea Education Association. And I spent 7 years there. It's in Woods Hole, Massachusetts. And I was working with undergraduates who would take a semester away from their regular university and come and study oceans with us. They would learn how to sail and navigate, as well as do oceanographic research. And that was super fun. And then in the middle of this decade, I moved to UBC. I teach climate change here, usually at the first and third year undergraduate levels. And I teach environmental science as well, usually second and fourth year kinds of levels. And then in this most recent decade, I did, as noted, I created a free open online course about climate change. This was with my really amazing colleague, Dr. Sara Birch, who was at UBC at the time. She is a climate policy expert and is deeply involved in national and international level conversations about climate solutions and what we're going to do about the climate crisis. She's now at Waterloo, and subsequently shifted that course to just a climate science course, which was offered on edX. And later I'm going to show you a little bit from that course. So I'm pretty sure that most of the people here have seen these figures, and to me, they illustrate that climate change can be pretty terrifying, right? We see this increase in the red going on over time. And you know, my students and I talk about this, and they can examine the data and point out that there's more warming over land than over oceans. There's more warming at high northern latitudes than the global average, and I look at these patterns of change and discuss the fact that the surface temperature has gone up by a little over a degree since pre-industrial times. And this, of course, we could look at the data back to the early 20th century. So if you go to this link, it would go back to 1901. And I just show these 5 panels primarily because, as I pointed out, they pretty much show the span of my life so far. And so it's maybe 60% of a lifespan if I make it to life expectancy for people of my demographics. So, 2/3 of a human lifetime, and there's really been a lot of change in that time. And so, maybe for you, it's data like these. Maybe these speak to you and play into your perceptions of the risks that climate change poses to us. Maybe they help determine your decisions to participate in dealing with the climate crisis. But that's really just maybe, and maybe it's not the data at all that really matter to people. So I think of a couple of goals of climate science education. The first one I think is the most important one. More people with more expert-like understanding of how Earth's climate works. That would be really cool. More people able to evaluate scientific evidence and explain that evidence. Maybe this would shift norms or shift the conversation, because we all talk to our friends and family, we talk to our neighbors, we talk to people at work. And those, if people knew more, maybe they would be talking to the folks in their groups and spreading that understanding. And there's kind of an assumption here that if one had more understanding of how Earth's climate works, then maybe you'd have the ability to do things like evaluate whether proposed solutions are actually aligned with the problem. So maybe you're better equipped. And then sort of as a stretch goal, maybe you would choose to be part of solutions and actually be involved. And then the second one is, of course, that science is amazing. And for some people, it's going to be fascinating to learn how our planet works. This is where we live. And I just want to point out that most people who are teaching climate science in colleges and universities are in the category of people who are fascinated by the science. And sometimes we forget that our students are there for possibly other reasons. And they may not have that awe and amazement and delight and satisfaction in learning. And maybe they have some other motivations for being there. So on a practical level, I'd like to ask these kinds of questions. Can more people holding more expert-like ideas about how the climate system works, can it actually help us deal with it? What role does climate science education have, and how big is that role compared to other factors? And I think we might agree that it does matter that we act as a human society, but does it really matter if people understand the climate science? And of course, coming from my position, I like to think so. It seems logical. But what I want to do is look at what kind of evidence we have that maybe that's true. So just a little bit about climate science education. We can demonstrably help students shift toward more expert-like mental models about how Earth's climate works. This is an example of some work I did with Anna Gold. We were testing an intervention about students changing their ideas about how the greenhouse effect worked. And this was our measure, our pre and post measure of what students actually said that they thought. So what we have is two concept sketches here. They're both by the same student. The one on the left is before the educational intervention, and it has some really nice pictures. I love the sun in this picture. It has a lot about reflection of radiation going on. Fundamentally, the system that's described here would actually lead to the planet overheating. And there's quite a bit of care taken with some things that are really extraneous to how the greenhouse effect works. They're not inaccurate. Here, trees help remove CO2 from the atmosphere, which is correct. Here's some sources of human emissions of carbon, cars and planes and cities and factories. So they spent quite a lot of time on things that are peripheral and accurate, but not necessarily that relevant. And then after instruction, this is the same person answering the same question to do a concept sketch. And they have a much more expert-like, sorry, I've got my mouse in the wrong place. They've got a much more expert-like idea that they've represented here in their sketch. They have infrared radiation coming from Earth's surface. They have it being emitted by greenhouse gases that have properties that allow them to absorb and emit infrared radiation. And they have that radiation going in multiple directions. And this is a much more expert-like kind of explanation that happens. And I just want to point this out because there is a lot of literature about how do we get people to learn the climate science. I would say there's also collections of educational approaches and lesson plans. Good ones are curated by the Climate Literacy and Energy Awareness Network, which are vetted both for pedagogy and also for climate science information. We also talk a lot in climate science education about how learning climate science is hard because learning what you need to know about how the atmosphere functions is not intuitive. And I just want to show this as well, because this is one of the fundamental problems we have in helping people understand climate science. And this is conceptually from John Sturman and Linda Booth Sweeney. And they studied how we tend to mess up when we're thinking about stock and flow problems. And I've used modifications of their tasks with my students. I really like them. And I know that they've been brought up before in this conference. I managed to sneak into a couple of the talks, but I wish I had been able to see more. Anyway, the issue with this is that we tend to dissociate, we tend to associate changes in a stock, in this example, the stock of carbon in the atmosphere, which can also be expressed as the atmospheric CO2 concentration. We tend to associate the changes in that with the changes in relevant flows. And so in the upper panel here, we have 200 years represented from 1900 to 2100. The upper dark line is the historical inflow from human emissions. And then the lower dark line is the outflow. And this is, of course, uptake by things like the oceans and the land biosphere. And then we're thinking about a scenario where, let's just say that the inflow flatlined and stabilized in 2015, and the outflow also stabilized in 2015. And many of us, our intuitive response for what would happen then to the stock is that it would also flatline, because we're kind of pattern matching here, and we want the stock to match what the inflow and outflow are doing. Because, hey, look, you know, they were all going up over here. These patterns here match. But once we stabilize things here, this isn't actually right. And I think you probably know that. So this is what really happens, because, of course, every single year, the inflow is greater than the outflow. And so we're constantly adding, we're having a net addition to the stock of carbon. And so we have this problem where we think that, oh, if we just flatten these curves, then we'll flatten the atmospheric CO2 concentration. That's the problem with the greenhouse effect. So that would be good. But what really happens is it increases. So we do talk about net zero lately. And that, of course, means that these two things are equal. The inflow and the outflow are equal. So either the inflow has to come down or the outflow has to go up. They have to meet each other somewhere. And once we do get there, then we'll get to this flattened curve. Now, of course, we all are much more familiar with flattening curves from the pandemic. So that's helpful in terms of lots of people thinking about these things. But the problem, of course, is where are we going to flatten the curve? Is it going to be here? Is it going to be up at 450? Is it going to be up at 480, 500? That's going to matter where that flat lines. And of course, as I think this group knows, the CO2 doesn't come out of the atmosphere particularly fast because it's reliant on processes that don't act particularly fast. So not intuitive, complex, but you know, we can, as educators, we can create and facilitate evidence-based and student-focused interventions that help people think through these types of problems. It is really a special topic because it relates so directly to arguably this largest challenge that we face as humans in ways that not all the topics we teach in post-secondary really have. So, you know, does learning this science, does learning to deal with this kind of thinking, does it have any spillover impact? Does having more people able to explain the greenhouse effect or explain sea level rise or carbon cycling in some kind of scientifically reasonable way, does that help us deal with the climate crisis? And so I would like to ask you to do something here. And I want you to write in the chat, but just don't hit return quite yet. So think about what concerns you most about climate change, whether the thing is local or global. You can pick another scale if you'd like, that's fine. And just in the chat, write something. For example, if the thing is local, write local and then what that impact is. And I think I'll give you about 20 seconds just to write something. Don't hit return yet. We're going to hit return all at once. So you've got about 5 more seconds. Okay, you can go ahead and hit return. Okay, so we have things like population extinction, small developing island states, and I assume impacts of climate change on those states, increased inequality, so social human inequality, future biodiversity, okay, living things around where you are, 16, okay. Species, war and disease, species loss, war and diseases, flooding, okay, that can be really quite local. Food shortages, of course, we have a global supply chain for food, and that really is important. So we have a mix here of global and local concerns. And what I'd like to ask you next is, here, climate refugees. What I'd like to ask you next is just, again, write in the chat, but don't hit return right away. How well do you feel you understand the science behind that impact that you identified? And I'll just give you maybe 5 more seconds because that should be pretty quick.
Can you just make a little note to participants when you write in the chat, if you want everyone else to see, you have to make sure you're sending to all panelists and attendees so the other participants see your answer as well.
Thanks for that. Okay, you can go ahead and hit return. Okay, so we have some goods, very well, a 2 out of 10, very well, fairly well, some basic knowledge, not really. I know I can know a lot more, a little, 7 out of 10, good understanding. So we have a range. I think you all are probably toward the top of the range of understanding the climate science. And some less so, some feel less confident in their understanding of the climate science. And so just do this to illustrate, of course, that you can be concerned about something to do with climate change and not understand the science very well, and also recognize that you don't understand the science. So how much science do you need to understand? And most likely it really depends. It depends on the situation that you are in, where that's going to matter and how much it's really going to matter. So thank you for that. Okay, so I want to tell you a little story. And this is about a decade ago. And I was at the American Geophysical Union in 2011 in December. And I think you've probably seen these data like earlier in this conference. So this will probably be a review. I'm not sure. I know that Dan Kahan has been mentioned. So I was there at a panel. Dan Kahan from Yale presented some data essentially showing that people's perceptions of the risks of climate change didn't have very much to do with their scientific literacy. And so this panel that's shown now on the left essentially shows an information deficit model where the hypothesis would be that if you had low science literacy, then your perceived risk of climate change would be low. And if you had higher scientific literacy, that risk would go up because you would learn about the science and you would think, whoa, that's really scary. So, and then he showed what he actually found with the population that he and his colleagues studied and found out that with the measure of science literacy that they had, they showed that people with greater science literacy actually had a slightly lower perception of the risk of climate change than people who didn't score as well on the science literacy measure. And so I was sitting there in the audience a decade ago. He essentially showed these data and I was thinking like, whoa, this is what I do. I teach climate science, and is that essentially useless as a tool that could help us move as a global community toward action? And is it in fact making things worse, right? So is becoming more scientifically literate actually making people feel climate change was less risky? And so I recognize that, you know, it's personal for me, and I recognize my position in kind of interpreting this. It's a little bit like when the physicists, I don't know if you have heard about this, but the physicists found out that if they taught people a first-year physics course and they asked them about their views on how science works at the beginning and at the end, they found that taking a first-year physics course actually worsened their thinking. They became less expert-like about science than they were before the class. So it's like, can we do no harm? So anyway, so Kahan's data pretty much says that the knowledge deficit model clearly doesn't work. I think there's plenty of evidence that it doesn't really work. Being more scientifically literate doesn't lead to higher perceptions of risk of climate change to society. And so, you know, what is important? And he also looked at people's worldviews. And here is the hypothesis that people who would score higher on the egalitarian communitarian end of the spectra of worldviews, that they would perceive climate change as a high risk. And the hierarchical individualists would actually kind of have an information deficit model going on. And that also doesn't really turn out to be true. It's pretty true for the egalitarian communitarians. They're viewing the risk of climate change as high regardless of their science literacy. And the hierarchical individualists pretty much view the risk of climate change as low. But really the interesting thing here was that the more scientifically literate people were, the more polarized they were. So, you know, again, this kind of makes me question what I'm doing. And And one thing about this, though, was that they were not looking at climate science. They were essentially looking at a literacy measure. And they had some questions like, what's the probability of getting a disease? They had like the trick question, I think kind of a trick question about, you know, the bat and the ball costs $1.10 and the bat costs $1 more than the ball. And so how much does the ball cost? It's one of those questions where you've got the intuitive response, which is wrong, and then you have to think about it and you could figure out what the answer is. And some sort of basic literacy questions like, you know, how long does it take for the Earth to go around the sun, or what's the role of antibiotics? So anyway, they weren't looking at climate science as a measure. So what if we did have a test of climate change knowledge that was validated? Could we then, one thing we could do is we could look at what is the general understanding of people in terms of climate change conceptions. And then another thing we could look at is whether or not understanding climate change conceptions had any role in risk perception or was related to risk perception in any way. And how did that, how important was that compared to things like people's values or worldviews or demographics? And you know, there is an assumption here that something to do with risk perception may lead to action. And I certainly can leave that to other people who study those connections and those models of behavior. I did find Tom Dietz's talk last week pretty interesting in thinking about the models that connect to these. So what we did, we set out to develop a validated test of climate science knowledge, and this was work that was done with 4 people. It's Julie Lebarkin, Anna Gold, me, and Karen McNeil. And I'd been working with Anna Gold earlier at the undergraduate level. And Karen McNeil and Julie Lebarkin had been working together looking at high school level students. And so we set out to develop a validated test of climate science knowledge. And I'm just going to list some things here that we were aiming for. We wanted the test to be able to do. So we certainly wanted it to have content validity. It needed to be aligned with the discipline. It needed to have a range of conceptions that were spanning a reasonable range within the discipline. It needed to take into account expert views and student views. And so we did things like review literacy documents like the Essential Principles of Climate Literacy. There's a lot of published literature about student misconceptions in climate science. We looked at items from existing instruments, and we underwent an iterative revision process to get to consensus on some items to test with all of us. We needed the test to be understandable by a lot of people. And the test that we ultimately did design has an ease of reading at grade 8-9. So this is accessible to many adults. And it's certainly not necessarily appropriate for younger children, but it has a reasonable level of reading ease. The really critical part is that we needed to, sorry, one more, before the really critical part. We did want the test to measure just one trait, right? We didn't want to have multiple traits measured in the same instrument, and it was needed to be climate change understanding, and we validated this with principal components analysis showing that we did have one principal component. We weren't testing multiple constructs. The critical thing, though, we really needed a test that would differentiate participants based on their ability with climate science conceptions, and we needed a test where the question difficulty was spanning the range of the participant ability. And so the test validation we did here was grounded in Roche analysis, in which we're modeling both the characteristics of the test takers and the characteristics of the test questions. And last, we need a test. We need the questions need to perform equally well, regardless of demographics. And for this last one in the analysis, what we did was we looked at test takers who had similar abilities but different demographics. And we looked at whether there was differential performance on particular items. We were able to look at binary gender and race. One of the items that we originally had did show differential performance, on both of these actually demographic variables, and we removed that. But we do need a test that doesn't show bias in how people respond. So we came up with a 21 question test, and thank you to those of you who tried it out on the survey. And I'm going to talk a little bit more about some of the ways in which we looked at whether the test was acceptable for the purpose we intended it for. One of those was looking at item response characteristic curves. This is an example of one with one of the questions that's on the test. And on the horizontal axis, we have the participant ability going from low in the negative numbers here up to higher on the right in the positive numbers. And we want a test where the probability of people choosing the correct answer or the incorrect answer is associated with their ability. So on the vertical axis is the probability of someone choosing a particular answer. All of our questions have an I do not know option, so people don't feel the need to guess. They can choose I do not know and know that that's the right answer for them. And so we should see that the probability of choosing I do not know should be high when participant ability is low, and it should decline as participant ability goes up. And that's what we do see. For the correct answer, it should be low when participant ability is low, and it should increase with participant ability. And that's another thing that we see in this question. For other answer choices, there should be a range of participant ability where that answer choice is attractive. And for example, here's answer choice A, it's in the gray line. At really low participant ability, they're unlikely to choose it, but that probability goes up. And there's a range of participant ability in here where they've got a decent chance of choosing that answer. And then the probability of them choosing that declines as the participant ability goes up again. And I am having slide issues again. So we've got these kinds of patterns of the probability of people choosing answers based on what their ability is. One of these has a really low, this is answer D, has a really low probability of anyone choosing it all across the board of participant ability. It's virtually zero as we get to higher abilities. So we wanted response curves like this. And we found, for example, that at least one of our questions didn't show something like this. We had a question that was really, it was trying to get at a too expert a concept, and the question didn't perform well. We had people answering correctly for probably not very good reasons, and incorrectly also. So it didn't seem to meet that criterion that the test question actually aligns with participant ability. Okay, so the next thing that I wanted to show was about whether the test aligns, the difficulty of the test aligns with people's ability. So it's not really very helpful if we have a test where all the questions are of similar difficulty, or a test where all the questions are too hard or all the questions are too easy. And so what we have here is a scale, vertical scale, that's in units of logits, which don't really matter. But we have on the left of this vertical line, we have a histogram of sorts showing the abilities of the participants on whom we validated the test. And we have a lot of participants here in the middle range. And then we have tails going on there. Some people who were really had quite high abilities and some people who had quite low abilities. And then on the right are the positions of the different questions in terms of difficulty. So the less difficult is down low and the more difficult is up higher. And what we see is that we do have a pretty decent spread of the difficulty of the questions here. And it aligns pretty reasonably with the distribution of the people's ability. So essentially, if you took a person who had an ability here and you look at the question that's at the same level, that person would have about a 50% chance of correctly answering that question. And that person would have a lower and decreasing chance of answering questions as you go farther up in this difficulty scale. And that person would have an increasing chance of correctly answering the questions that are down here toward the less difficult end. So that's how these are related. So we do have this is a test. It's imperfect, but we think it actually aligns pretty well. We have a gap here. Maybe we could come up with a question that filled that gap in terms of ability and then would be able to differentiate people up here. We do have kind of a top-heavy test. There's a cluster of fairly difficult questions. There are some people who are down here in an area where we don't have any questions that are at their level of difficulty. So anyway, this does provide us some additional evidence and confidence that this test is aligned with the abilities of a population. The distribution seems spread out, and it seems to cover almost the full range of ability of the people. All right, so I didn't actually tell you who we validated this on. The first population listed here was the group we used to validate the test and as the source of the last two figures. We used this population, we got about 1,000 people to answer our original draft test questions using Mechanical Turk. And this is a system where people are paid a small amount of money to take surveys. It was a US population. We had some parameters, some filters to filter out people. One of those was you had to be over 18. So we had a sample that was between ages of 18 and 75. Average was about 35 years old, 47% female, only 4 identified as transgender. So we couldn't do a lot with those identities. And the second 2 listed here were populations in which we implemented the test. So for the Mechanical Turk sample, we asked them the original questions, and we asked them a risk perception question to assess their risk of climate change. We asked them some values measures from Linda Stegg, which answer your rating statements, and we're then able to give them a score on values for egoistic, altruistic, biospheric, and hedonistic. We asked them Kahan's worldviews questions, and we asked them demographics. And the purpose was then to try to be able to see whether this climate change conceptions measure would actually have a significant role in risk perception and how it would relate to all of these other items. So just going back to Kahan directly, briefly, once we use our climate literacy test, we do find that people who score lower on that test do have a slightly lower perceived risk for climate change, and people who score higher on that climate literacy test do have a slightly higher perception of the risk of climate change. So this does counter Kahan's work with using his scientific literacy test that wasn't looking at climate change conceptions directly. So as an educator, this is like, phew, okay, maybe there's something that does matter. But what we then did was we used a regression analysis to try to estimate risk perception and what was related. And the big things that come out are that having biospheric values is positively associated with risk perception, as is sympathy toward environmentalism. Having individualist worldviews was negatively associated with risk perception. So this goes along with Kahan's work. And there's some other worldview and political stance and age. Those hierarchical worldviews, politically conservative and being older, were associated with lower risk perception. And there's a little significant impact of climate change conceptions on risk perception in this Mechanical Turk population, which is representing sort of US general. And so, we do have climate change conceptions actually contributing to risk perception in here, but other things are clearly more important. So we took the test and we implemented it in a post-secondary university setting. This was at a large American university in the Southeast, and they were enrolled in a earth science course. Climate science was part of it, but it wasn't the main focus. It wasn't a climate science course. There weren't any learning goals that were related to risk perception in the course. And so what we gave them was the climate change test, the question about risk perceptions, and then questions about values, worldviews, and demographics. Those last 3 were actually only asked in the pretest. And that assumption there is that those won't change. And I think that'd be interesting to actually probe a little bit. But we looked at their pretest scores and their post-test scores on the climate change and risk perception. as well, and also looked at what mattered to them for risk perception. So climate change conceptions actually show up as a significant and larger factor for this population in terms of being related to their perceptions of risk. Biospheric values again show up. And in this population, about 3/4 of them identified as white. And so being white was associated with a lower risk perception in this population. They did improve their scores, both on the climate change conceptions, and they changed their risk perception between the pre and the post test. So they increased their climate change scores by about a standard deviation and their risk perception by about half a standard deviation. So they are changing their risk perception, it looks like, at the same time that they are becoming more knowledgeable about climate change. One interesting thing was that students who were not majoring in science, technology, engineering, or math, which is STEM, those students actually showed a greater shift in risk perceptions than the students who were in fields that were STEM fields. They didn't quite catch up in risk perception to the STEM majors, but they had a bigger change over this time. Okay, the third population that I wanted to talk about was people taking this free online course about climate science. This was offered on edX several times with cohorts, and then also in self-paced mode for I think about a year or so. And part of this course was really asking people to delve into their local environment. And this is a map of people who were enrolled in the course and who also contributed to the course content by doing homework essays. And we asked them to write about something going on in their local area that was an impact of climate change. And we also asked them, there were 2 essays in the course. The second essay was about writing about something to do with the carbon cycle and climate change that was relevant in their area. So it encouraged people to look around them and find something that was focused and graspable, and then also contributes content to the rest of the participants who are scattered all over the world. And this is the kind of content that a single instructor could never possibly come up with. But this sort of crowdsourcing mode really does get us to be able to have people connect to the climate change issues all over the world. As you all know, climate change is overwhelming. It can really seem overwhelming. And so the ability to kind of go local gives us a little bit something more concrete to grasp onto. And it may also turn up opportunities for people to get involved and do something in their communities. So with this group, we ran the regression trying to estimate risk perception with almost 2,000 people who completed the pre-survey at the start of the course. And we came up with biospheric values again being important, sympathy toward environmentalism, being politically liberal, those were important. Slightly less important, being female. Climate change conceptions, again, had a small but significant impact on risk perception, or connection, sorry, to risk perception. And also altruistic values showed up in this as significant, which I find interesting and maybe worth exploring some more, particularly with the discourse that's going on today with Fridays for Future and with discussions of racial injustice. Are there avenues to explore where climate justice issues, intergenerational justice issues, or issues around vulnerable populations and the impact on them, are those something motivating that gets at people's perceptions of risk? I do want to point out with this population, we didn't ask the worldview questions from Kahan because if you read them, some of them are actually quite North American centric, and the context probably is not appropriate for all over the world. Okay, so this is how these folks did in terms of the pre-post. And if you've ever been involved in a free online course, you know that a lot of people start out and many fewer actually complete it. So we've got 107 people who actually completely did the pre and post surveys. Those people did improve their climate change conception scores, and they also increased their risk perception, though they're kind of topping out a little bit. And I think I'm over time. I'm sorry. I did want to show you this
We have half an hour for questions, so you can, finish your presentation and then we'll get to the Q&A.
Okay, thanks. I can't actually see anybody. So I do want to say thank you for indulging me, those of you who took the test and rated your values. This is the results from what I saw on Sunday. So there's a range of scores of people in this group. You were 36 of you answered the questions. You actually scored quite high on the climate change conceptions compared to the other groups we've looked at. And you all have quite high risk perception, right? We've got 10s that are across the whole range of climate change conception scores. So we might be kind of hard pressed to connect to anything between climate science knowledge and risk perception in this group. But thank you for doing that. So in the three groups that we looked at, these are things that come up in all of them. Biospheric values turns out to be important, and climate change conceptions, but much more important in the university student population than in the other two, which were more sort of general population, though, people who sign up for a free online course about climate change, they're not necessarily general population. And then the question really becomes for me is, what should we do as climate science educators? I do think it's clear that we can teach climate science in ways that can help move people toward more expert-like understanding. That's not a given, but we can do it if we do it well. Climate science knowledge based on this work, and I realize this is only a few examples, it looks like it's usually a minor player in predicting people's risk perceptions. It seems like potentially post-secondary could be a really good time to learn climate science, where there seems to be a stronger connection between knowledge and risk perception. And maybe these are people of a certain age whose perceptions have not solidified as maybe we solidify as we get older. And I think incorporating opportunities to reflect on values, particularly biospheric values, incorporating those into climate science education could help us shift people's perceptions of risk. And I kind of want to come back to where climate science is being taught in post-secondary. It really is likely in science departments by science faculty who have these long-standing cultural norms and might be less likely to explicitly address personal values in the context of a university course. There are certainly exceptions to this. But I wonder if we're shying away from addressing values when we teach about climate science. And if we are, we may be really missing out on opportunities to tap into what's really important for students and also what's important for climate action. So thank you.